Hello students, welcome back. Um, this is the last chapter in the syllabus. Um, the name of the chapter is Reactions of Synthetic Importance. Uh, Reactions of synthetic importance means these are the reactions um, which are useful for the preparation of maybe medicinal compounds or preparation of uh, for the preparation of intermediary compounds or intermediates, or maybe of importance for the analytical purposes. That's why they have named these reactions as the reactions of synthetic importance. Actually, there are 9 reactions in this. Um, as you can see on the screen, there is one reaction of oxidation kind. So oxidation reaction, you have open reaction, and there are 4 reduction reactions. They are, one is metal hydride reductions using sodium borohydride or lithium aluminum hydride. Then Clemenson reduction, Birch reduction, Wolff-Kishner reduction. These are the 4 reduction reactions. Then there is one replacement reaction, that is Dakin reaction. There are 2 rearrangement reactions. They are Beckmann rearrangement and Smith's rearrangement. And there is one condensation reaction, that is Claisen-Smith's condensation. So these are the 9 reactions that we are supposed to study in this syllabus. Um, of course, there are oxidation reduction reactions. Let me remind you about the oxidation reduction discussions that we had in our previous classes. Let's see what are oxidations and reductions. Oxidation, as you know, oxidation is addition of oxygen, right? Addition of oxygen, okay, or loss of hydrogen, or even loss of electrons, or loss of a pair of electrons. We also had discussion about this oil, that is oxidation is losing electron or ring. It can be there is another short form for that reduction is gaining electron. That is for the reduction, one for the reduction, oil and ring. So reduction is the reverse of oxidation. It is loss of oxygen, right? Then hydrogen, addition of hydrogen, or gain of, again, addition or gain of electrons, or pair of electrons. So these are in general what are oxidations and what are reductions. Just to remind you on that, because we are going to study the oxidation reduction reactions here in this chapters. Also, let's go through this general thing, like suppose um, this is your alkane, and in that it is ethane, right? Suppose ethane, we will create a double bond here. That means we have to remove the hydrogen, right? Removal of hydrogen is again oxidation, right? Oxidation. Then again you remove two more hydrogens, right? So again this is the oxidation. So from alkane you are going to get alkene. Alkane to alkene is alkene, and again alkene to alkyne, alkene to alkyne oxidation. And the reverse is reduction, right? Alkyne to alkene, you have to give the, you have to do the hydrogenation, you have to add the hydrogen. Adding the hydrogen is a reduction, right? Again you add the hydrogen for alkene, right? You add the hydrogen and you're going to get the alkane. So that is the reduction. So alkane to alkene, alkene to alkyne is oxidation. Again alkyne to alkene and alkene to alkane is a reduction. Alright, one more thing. Again CH2, or you take alkane, or let's do this. CH3 alkane, right? Convert this to CH3 CH2 OH, alcohol, and convert this to aldehyde. Okay, I'm just writing in general. It's not that I took this and I came across like this, but in general I'm trying to, and that is ketone, right? Again convert that to carboxylic acid, right? Here again you can convert to like ether and ester. Okay, all these conversions, alkane to alcohol, alcohol to aldehyde, aldehyde to um, your ketone or ester or ether, and again conversion of that to your carboxylic acid. These are oxidations. So you are going on adding oxygen, or you are removing the hydrogen here. You are removing the hydrogen. So these are oxidations. Again, the reverse of this conversion of carboxylic acid to ketone, ketone to aldehyde, aldehyde to alcohol, alcohol to alkane. Those are reductions. Those are reductions. Those are reductions. Okay, now the oxidation or reduction, it's not like this. From this has to form from this. This can be formed. Or from this directly, this can be formed. Or from this, from alkane directly, carboxylic acid can be formed. So those are also oxidations. So the reverse, even carboxylic acid to alkane, or ketone to alkane, that is also reduction, and it all depends on how strong the oxidizing and reducing agents are. So this is one thing you have to remember. Okay, you can take a screenshot of it, you know, just for the remembering and recalling it. Anyway, so after this, let's go for the individual reactions. The first one we are dealing with is the oxidation here. First, this is the only oxidation reaction among the nine reactions, that is opener reaction. The first thing is like a definition, or what is the reaction going to do? What is going to convert to what? Okay, using the oxidizing or reducing or any other reagents. Then we are going to study the mechanism of that reaction. Then we are going to study the application of that reaction, where it is useful, where is the situation that it is very useful. And then we can also study like the limitation of that reaction, the drawbacks of those reactions, or any modifications that we can do for that reaction for the better results, that also we can study. So these are the things we have to study in these reactions, in these individual reactions. First one is a opener reaction. Opener reaction is nothing but conversion of a secondary alcohol to ketone. So here we are converting secondary alcohol to ketone. So it's going to happen in the presence of aluminum tertiary butoxide. So that is the reagent we are taking here for the oxidation reaction. And this reaction is going to happen in benzene or toluene solution. Okay, this medium is required. And one more condition is it should have, the reaction should contain excess of ketone. Usually it is acetone or cyclohexanol. So you need ketone for this. That is to move the reaction forward. You need ketone. Those are you can take either acetone or cyclohexanol. Now, so this is what the reaction is. Now let's see the uh, chemical formula wise. What is this reaction is? Okay. Now, it says it is the conversion of secondary alcohol to the ketone. Right? Now, here is the isopropyl alcohol. Isopropyl alcohol is a secondary alcohol. Here is one primary group attached to the carbon atom that is attached to the alcohol. Right? If this is hydrogen, so then it is a primary alcohol, but there is one more here, the second group is attached, so it is a secondary alcohol. So here it is a isopropyl alcohol. As I already told you, you have to use ketone, excess of ketone, acetone, right? We are using acetone here, right? So you are reacting that with the acetone in the presence of aluminum tertiary butoxide. This is aluminum tertiary butoxide. You can see the structure here. See, it is thrice, and to that again you have to three times the aluminum 1 2 3 O O and right again C in the bracket CS3. This is aluminum ion. Again you have to attach those in a similar way. This is aluminum in a similar way. So that is nothing but aluminum tertiary butoxide. What is going to happen? This isopropyl alcohol, which is secondary alcohol, is going to convert to acetone. Secondary alcohol is going to get converted to acetone. And again, isopropyl alcohol is the your side product here, byproduct. Okay. Now what is happening here? Now see, this is the alcohol group, that is, and this is the ketone group, right? What is going to happen? This is going to come and sit here, and this is it's the exchanging of these groups are going to take place. It is going to be clear here in the next, in the general reaction formula. So this is the secondary alcohol, two alkyl groups there attached to the carbon, that is attached to the alcohol group. This is secondary alcohol. So you are taking acetone, right? This is aluminum tertiary butoxide. So it is getting converted to, now you exchange this, put this in here and put this in here. So putting this in here, instead of secondary alcohol, on that you are going to get the ketone, right? So it is getting exchange and you are getting isopropyl alcohol here. So it is the conversion of secondary alcohol to the ketone. So this is the reaction. Now let's see what is going to happen. I mean, what is the mechanism, how that is going to happen. How that is going to happen. This is the mechanism. Alright. Now this is the secondary alcohol. Right? This is aluminum tertiary butoxide. It is going to happen in the presence of aluminum tertiary butoxide. Right? Now this oxygen will have the pair of electrons. Right? It is ready to give the electrons. It has the electrons on it. The aluminum being positive, electropositive, so it's going to attract those electrons, and there is going to be a bond formation here between secondary alcohol and aluminum tertiary butoxide. So here there is the attachment, so we are going to do the attachment here, right? we are going to we're going to attach this. So what is going to happen, these electrons, they are going to jump onto the aluminum, right? Aluminum was actually neutral. There was no charge on it. It is like partially positive. It was going to attract the electron, but there was no charge on it. So now, because of these extra electrons, only when there are extra electrons or removed, adding the electron or removing the electron, then it will get a charge. We are going to give them the symbol. So that's why now, because the aluminum got extra electrons, so it is going to uh, um, get negatively charged. So it is negative over here. So because its oxygen is giving out the electrons, so its proton gets exposed, so it is going to be positive. So it is getting the positive charge. Okay. Now what is going to happen next? Because aluminum has got negatively charged, and these bond electrons, right? This bond electron between Al and O, because aluminum is negative now, so it is going to shift to the oxygen, right? And it's going to come out actually. It's going to go out. While going out, what will happen, because the oxygen is positive here now, these are the electrons between O and H, they are going to get attracted to the oxygen. That's why this hydrogen is going to go out, and this hydrogen is going to go out, and it is going to join with this and join with this. So you are going to get tertiary butyl alcohol. This is tertiary butyl alkoxide. So it is now alcohol, right? By getting that one hydrogen, so it is going to get converted to tertiary butyl alcohol. Right. Now, by removing this H and this tertiary butyl alkoxide, we will write the structure here, the new structure. Okay, there is no H here, right? And there is no this side chain over here. Now, what is going to happen? Now we have acetone in the reaction mixture, right? So we are supposed to take excess of a ketone, like I said before. So we are using acetone here. So what is going to happen? Acetone, oxygen, it is negatively charged. It will have more of the electrons or unpaired electrons. So those will get attracted to this positively charged or positive aluminum. Okay, positive electropositive aluminum. So now that is going to form the bond over here. As you can see here, this is the bond it's going to form. That this is the bond it's going to form, and because of gaining those electrons, aluminum is going to get negatively charged, and oxygen is going to get positively charged by losing these electrons, right? So here this bonding will form. So let's see what is going to happen next. Now because this is negatively charged here, now the bond, the electrons from the between the bond between oxygen and aluminum, that is going to shift to the other side. It's the two two electrons, those are going to shift to this side, and it's going to form a bond here. It's going to form a bond here, and from that this keto group will form, and from that keto group is going to form. Now what will happen to here, because the oxygen is positively charged here, this bond electron, the bond over here, the bond, one of the bonds over here between oxygen and carbon, it's going to shift, the electrons are going to shift over here. And what will happen is, because the electrons are going to shift over here, being it is negative now, having more of electrons, and this electron, this proton, it's going to get attached over here. It's going to get attached over here to this oxygen, and with that this is going to form, this alcoholic group is going to form, and you are going to get the isopropyl alcohol. So this is the actual mechanism that is going to happen over here. So that is the conversion of a secondary alcohol to the ketone. This is the mechanism of the conversion of secondary alcohol to the ketone using a Oppenauer reaction. Alright, let's go next. So this is the step which I just explained, and let's look at the application of this reaction. So where is it useful? Uh, Number one, it is specific for alcohols, like especially secondary alcohol containing oxidizable functions. So where it is useful in converting olefinic double bonds. Olefinic double bonds. It's not just a conversion. If the olefinic double bond chain has got alcohol, so it is going to convert that to the ketone, right? Now why are they mentioning this over here using tertiary aluminum butoxide? Now why are they mentioning here? Because even this can, these have to I mean nothing is going to happen to these double bonds. So as intact, by intact you can change the olefinic double bonded alcohol to the keto form. That is the advantage, I mean that is the usefulness of this reaction, and it is also used to convert phenolic groups. Alright, next used in the synthesis of steroid ketone, steroid ketones, so used in the synthesis of steroid ketones, useful in the preparation of the synthesis of cholesterol, right? Testosterone, progesterone, all these are hormones, and folinic acid, and some of the corticoids, the steroidal hormones. Right now, here is the cholesterol with the OH group, right? Here is the OH group, and this OH group using the open oxidation is going to convert to ketone group. So that is the advantage. Such a big chain, okay, such a big change during the opener oxidation. No other changes are going to happen to this ring. Only the alcohol group is going to get converted to the ketone. So that is the advantage of this reaction. Only the oxidation is going to take place at this alcohol. All right. So next is it is used in oxidation of formates to carbonyl group. Formates like formic acid. So this is format. If it is H over here, it is formic acid. So for it is used in oxidation of formates to carbonyl groups. So that is another application of it, the oxidation. And this is one thing to be mentioned. We have to mention this oxidation is exactly reverse of Meerwein Pondorf-Varley reduction. There is a reaction called Meerwein Pondorf-Varley reduction, and this opener oxidation is the exact reverse of that reaction. So this is about opener reaction, or opener oxidation, or opener oxidation reaction. So okay, there is one more thing left here. There is some limitation in this reaction. Some primary alcoholic groups have also been oxidized with the low. So it is supposed to oxidize only the secondary alcohol, right? Secondary alcohol. Sometimes what happens if there is a primary alcohol, so even primary alcohol is going to get oxidized to the extent 50 to 90%. So that is the disadvantage of this open air oxidation reaction. Next is fails with the molecules having basic groups in close proximity to um, hydroxyl group. So suppose you have let's not take this, let's take like you have OH group and you have some other group here like amine group. So when this when other groups are there in the nearby, in the proximity of this hydroxyl group, then it fails to do the reaction. The reaction may not happen. So that is the disadvantage or limitation of this reaction. So that is with the opener oxidation. Next, let's go to the Wolff-Kishner reduction. It's a reduction reaction. It converts aldehydes and ketones to alkanes, right? Ketones or aldehydes to alkanes. It's a two-step reaction. A high boiling point solvent such as ethylene glycol is used to provide the high temperature. This reaction needs the high temperature, so that's why they are using ethylene glycol as a solvent. And in this, nitrogen is produced part of the reaction. So nitrogen is a gas is going to released in this reaction. So what is actually the reaction is? So aldehyde or ketone going to get converted to alkene, right? So you are using hydrazine here. This is the hydrazine. This is the hydrogen, using hydrazine. And what else you are using? You are using alkaline condition potassium hydroxide, and you use the high heat. This is the hydrazone. This is the hydrazone. Alright. Now, what is happening in the reaction? So aldehyde or ketone, they are going to react with the hydrazine, right? You're going to get hydrazone. This is step number one. This is step one. And in the second step, for this hydrazone, in the second step, step 2, in the second step, this hydrazone is going to react with the potassium hydroxide, and you're going to get the alkane. So this is the reaction, conversion of aldehyde or ketone to alkane. So how is this going to happen? Let's look at the mechanism of this reaction. Again, let's go like step 1, step 2. The step 1 is same as the first one. We keep the same as what I explained earlier. So aldehyde or ketone, they react with the hydrazine, right? And they're going to form hydrazone, right? You're going to remove one molecule of water, right? These two combine, and we get one molecule of water there. This hydrazone, this hydrazone now reacts with the potassium hydroxide, OH of potassium hydroxide. Here also there is removal of one molecule of water using this hydroxide of potassium hydroxide, right? It is going to react with that, and you are going to get the water. And this is the structure you are going to get. So here what happens, this the one bonding electrons of this bond between C and N is going to shift to the on the carbon. So carbon is going to get the negative charge, and for that carbon, this the hydrogen of water is going to get attracted, right? This hydrogen is going to get attracted to this negative charge, right? So what will happen, this is going to be like H, right? That is what you got here, right? Now OH of this, the remaining OH portion of this is going to get attracted to this H, here again. The nitrogen of this is going to combine with the nitrogen of this, and you are going to get the nitrogen gas. So what is going to happen, this hydrogen is going to get attracted to the carbon over here, and it's going to form the hydrogen. Where is this hydrogen is from? This hydrogen is from water. This hydrogen is from water. The remaining OH from here is going to get attracted to this hydrogen from here, the hydrazone portion, and going to form water. Minus H2. Oh, this is not right. Minus H2. Right, and this nitrogen is going to combine with this nitrogen, and it's going to produce the nitrogen gas. Now what is going to happen over here? So these are all gone now. So these are all gone, and this bond electrons are going to go with the carbon, and carbon is going to be negatively charged. Now this carbon is going to be negatively charged, and for that again hydrogen of water is going to get attracted. This hydrogen of water is going to form this bond, this H, or it will get protonated. This hydrogen of this water is going to combine with the um, negatively charged carbon from here, right, and it's going to form the hydrogen bond. So that is the protonation of that. So thereby you are going to get the alkane. So this is how you get alkane from aldehyde or ketone. So how this is aldehyde, this is ketone. This is actually ketone. If one of R is H, then it is aldehyde. So the aldehyde or ketone can be converted to alkane using Wolff-Kishner reaction. So what is used in the Wolff-Kishner reaction? Hydrazine. You have to use the hydrazine at the first position, and in first step you are going to get the hydrazone, and again you are using potassium hydroxide, and using potassium hydroxide you are converting the hydrazone into the alkane, right? So that is the mechanism of the reaction. So next is the application. Where is it useful? Carbonyl group to methylene group. So you here the this reaction used in converting camphor to campaign. Camphor to campaign, right? Camphor will have this keto group here, and that keto group is removed. See, you don't see the keto group here after doing the Wolff-Kishner reduction using hydrazine, and here instead of potassium hydroxide you are using sodium ethoxide. Here the formation of hydrazone, right? So here this group is this it is converting keto group to CH group. This is CH. See, this is C, right? H2, CH2, and the bond again. So this is that group. This is methylene group. This is called methylene group. So it is useful in converting carbonyl group to methylene group. So next, synthesis of pyrols. Pyrols are heterocyclic compounds. So this is we are talking about the natural product pyrrole. So the degraded products of hemine, of hemoglobin and chlorophyll, okay, can be proved. Synthesis of those pyrroles, those natural pyrroles, can be proved by their synthesis, which in Wolff-Kishner reduction is used. That is the synthesis of oxopyrrole. Synthesis of oxopyrrole. This is something like each time when you get this, you have to prove that these are the degraded products of heme and chlorophyll. So you're going to do the reaction and get synthesis of you're going to prepare this oxopyrrole. You're going to prepare oxopyrrole, and you're comparing that by comparison. So you're going to prove that the degraded products are hemine and chloroform, and this is the just as an example. So synthesis of oxopyrrole is shown here using Wolff-Kishner reduction reaction. All right, next is it is used in elucidating the structure of estrone. Again, same thing. You are trying to prove that the compound is estrone here by using Wolff-Kishner reaction. When you use the Wolff-Kishner reaction in this, and the same compound is formed, see, ketone is removed here. Okay, ketone to again that methylene group. So ketone is removed, and here in this reaction, in here they are going to deprotonate this, remove the hydrogen. Anyway, each time when they do this reaction, if you get this product, this is this product. This product is nothing but 7-methoxy 1,2-cyclopentano of phenanthrene, where each time when you do the reaction, the Wolff-Kishner reaction on this estrone product, and you get the same product, 7-methoxy 1,2-cyclopentano phenanthrene, then it is like it is proved that it is a estrone product what they have got from somewhere else. Right? That is, it is used in proving or determining a compound. Right? That is the use of this. And so these are the two reactions that we studied today. One is opener oxidation, and the second is Wolff-Kishner reduction reaction. um, let's see if possible in the next video I'm going to complete, or I may take two more videos to complete the portion. Thank you very much, and let me know if you have any questions.